Great. Let me put the notes in the side. So, welcome everybody to the last lecture. Again, let me thank the organizers for uh, this nice set of lectures during these 3 days. So last time we talked about how the extension of the phase spaces can be done via this Stuckelberg trick, which consists in taking the radiative data here, and plugging in some extra field, which acts like a finite gauge transformation on the radiative data. Once we have that, we have this extended gauge vector, and that gauge vector we can make correspondences with subleading and leading charges. And the same has been done with gravity up to subleading order. So we have the radiative data for usual Bondi coordinates, and then we have an extra diffeomorphisms that only acts on the S2 part of the celestial metric, and that gives us a nice formula for how to extend these degrees of freedom. And the resulting phase space in both cases will be something like the original one times the parametrization of a space given by psi, or in the case of gravity, the extra diffeomorphism that we are adding. Okay, but this, just to make clear, for gravity, this has been done up to subleading order, which was the thing that we did last lecture. And for Yang-Mills, we managed to do it for arbitrary order n. But of course, there are you have to make sure that the charges that you obtain are the ones from the soft theorems to make consistency and so on. So the extensions can be done written in this way. But the interesting thing is that we can now go to the bulk. So try to understand this Stuckelberg trick from the bulk perspective, and then pushing the surfaces all the way to infinity is kind of an interesting point of view that has been taken by, for example, Laurent Friedel, Luca Ciambelli, among others, when studying local subsystems. Okay, so that will be the main point of today. And before starting with that, I would like to see if anybody of you has some questions.
Javier, just to make sure,
Yes.
these psi and zeta are the large gauge transformations of those fields, right?
These are new degrees of freedom that the large gauge transformation will act on them. So this psi, for example, is like is a large gauge transformation, but we are promoting it to a degree of freedom, so that the large gauge transformation that we want to act on the whole phase space will act in particular in radiation part and also in this psi.
Okay.
So the clear example in Maxwell, for example, so if we have, let's see a simple example. So we have that the angular part of the vector potential goes as 1 over of R0. So it has a finite limit when we go to Scri plus. And we want a large gauge transformation which goes as R epsilon1 plus epsilon0, and then subleading things. Then when we act with this on the radial part, this is a function only on sphere and U, well, and R, let's put here epsilon, and this is a function of the sphere, and this is a function of U and X. So these are angular coordinates. So the variation of the angular part will be R times dA of epsilon1 plus dA of epsilon0. And of course, this is violating our fall-offs for the radiated field. And how can we manage to accommodate these variations such that it doesn't violate the phase space fall-offs? Well, what we do is just create a new vector field, which is the radiated one plus the derivative of a function of the sphere. And this one now is the new degree of freedom. So now, when we act with some large case transformation, which is overleading, the action of this overleading symmetry on A will be only this part, and the action on phi will be just by translation. So it will be. So in that sense, that what we are doing is taking the problem away from the radiated part and putting it in another sector, which is the one that enlarges the phase space.
So at the level of the action is something like gauging, right?
Yes.
It's like putting a mu minus derivative of phi in the action, and that will be the new action.
Exactly. That's the new action. So it's like instead of writing the action for a mu, we write it for a tilde mu.
Yeah. And phi has no dynamics, right?
Phi, well, phi has, I mean, it's now once you promote it to the Lagrangian, it will have some equations of motion of its own, of course.
Ah, okay,
But
okay.
yes, the thing is that if you compute these integrals, so let's say the symplectic potential over a Cauchy surface, this will be the diversion because you have components in R. Yes. So the thing is that you want those divergences to vanish. So you have to renormalize in some sense
And you can
those
renormalize it.
expressions. Yes, you can renormalize them.
Okay,
Yes.
okay.
That
Yeah.
was for electromagnetism, it's easy because it's a linear thing, so you can just like see where are the polynomial divergences and kind of subtract them and prove that they are indeed divergences that you can subtract to the Lagrangian. But in Young-Mills, it's a little bit more work can be done. And in gravity, it has been done only up to the subleading part. And it has been done by Compare, Varnich, and Furich. Yeah. They renormalize the expression. Okay. Oh, so here, sorry, there was a missing part here because it has to be ordered up. So this is an example of how we extend the phase space. In gravity, and also in large scale transformation, this work by Donnelly and Friedel in 16, they work with what is called local subsystems. So what they say is, okay, you have a finite domain. So you have a finite domain, sigma. You have some diamond around sigma and the corner in here. And this is a subsystem of a larger spacetime. And they want to study how these large case transformations interact in this boundary here, in the null boundary. And what does it mean for this corner to have properties such as corner modes, what is called the charges that lives in C. If those charges and if those properties can be translated into Scray plus. And the thing is that it can be indeed. And this was the first work later by Luca Ciambelli and Robert Lee. They construct what is called in 21, but I think that there are some early works. They construct the universal embedding corner algebra. Universal corner algebra, which is the maximal algebra of diffeomorphisms that preserve the corner, or better said, is you took all the diffeomorphisms that preserve the corner, and from those diffeomorphisms you construct the maximal subalgebra spanned by them, and closed subalgebra spanned by them. And the thing is that when you do that, you have to take into account all the directions. So, for example, in bounding coordinate, you will have like the du, you have db, db. You have all the transverse directions along the surface. So you have to construct these diffeomorphisms fixing the corner. You see which ones preserve the corner, and then you construct the algebra generated by them. And what they found is that in general, if you have let me move this draw even further because we are going to need it later. So if you have m of dimension n and the corner has codimension k, then the group, the universal corner group is the following one, is the diffeomorphisms in the C n minus k. So this is like all the diffeomorphisms in the corner times G, L, K, R, and this times R, K. So that means we can identify each piece separately. So RK are all the directions along the DU, DBs, and all the things that are moving the corner in this direction. But these are abelian. And they move the corner, but they come from the brackets between the things that are inside this bigger bracket. Okay, so they form part of the things that move the corner, but nevertheless, they form part of the maximal closed solution. Then we have this part which contains all the boosts transversal to this surface. So these are kind of generated by the boosts and scalings. And then we have the transverse part, which is the diffeomorphism on the hypersurface, on the codimension K surface. So we have the diffeomorphism. Okay. And in our particular case, we are interested in 4 dimensions. In our particular case, we will have 4 for n and 2 for k. So what we are going to have is the diffeomorphisms in a sphere times GL to R times RK. Sorry, R2. So these are the diffeomorphisms that preserve the corner structure. Yes. And these are diffeomorphisms living in the bulk. If we took this limit all the way up to square plus, what we are going to do is, instead of living in a 4-dimensional manifold, these diffeomorphisms will be pushed to live in a 3-dimensional manifold. So therefore, n is going to reduce to 3. And the codimension now, instead of being 2, will be 1. So that means that when we go all the way to square plus, this algebra will turn out to be if S2 times R times R. So this is going from bulk to square plus. What does it mean? Okay, we can identify right away these terms from the previous lecture when we studied the symmetries. If you remember, we say, I'm just going to do a small note. So the generators above psi f, which were the supertranslation generators, were f du plus subleading, and the generators of superrotations were ba dA plus some minus du plus subleadings. And if you look at this, you see that this one corresponds to this direction because this superrotation is abelian and it corresponds to the abelian part of the reduced group. And the superrotations generated by this these here are the diffeomorphisms of the sphere. And we have this weird diagonal product with R, which comes from the fact that we are considering the divergence of V. So we are considering the Weyl weights of this vector when taking the sphere. Okay, and this is a reduction from the bulk to stripe plus. And we are reducing the whole group of symmetries to this new group, which we call the GBMS, remember? And there is no more to do in that sense. So if we study all the things that preserve the corner and we take their maximal closed algebra, then if we go to Scribe Plus, what we are going to have is the generalized BMS. So that's all. There's no new things. Because we are going to have the diffeos, the Weyl weight of the diffeos, and then the abelian part of this group, which is the super translation. But nevertheless, if we are in the bulk, we want to understand what happens with overleading gauge transformations. So overleading gauge transformations will be order R, order R squared, order R cubed. And what happened to those transformations? When they are in bulk, they produce some charges. What happens to those charges when we go to Scribe Plus? Of course, that we are going to have to renormalize them, but nevertheless, they are going to give us some information about the theory. Okay. Any questions so far?
Javier, in this generalized BMS group, in the diff S2, you have
Yes.
meromorphic functions, right? Not only.
No.
No, you are
No.
excluding those.
Yes, that's the main difference between the generalized BMS and the extension by Varnich and Dresser. So they consider meromorphic vectors, and that will give you the diff S1 times diff S1. And that's how they obtain this Virasoro.
Yeah, so this is not Virasoro.
This is not Virasoro. These are diff S2.
And diff S2 is SL2C or what is a group or what?
Diff S2 is a group of all the possible diffeomorphisms on the sphere, and you can take some subgroups, of course, but yes, that's not it doesn't contain any I don't know how to say it.
Seems like it's not related to the conformal group. Like one will expect that you can relate the conformal group of the boundary to the isometries of the bulk. Here, this is not the case because in the boundary will be 1 point and to the dimension 2 1 point, let's say 0, and you will expect that you had a Virasoro there, right?
Exactly.
Or something
exactly.
like that, or
exactly.
2 copies. Yeah.
2 copies. That's kind of the case with Varnich and Dresser compare and Varnich extension. So they have these 2 copies of Virasoro, and when the whole thing started. In this case, you have this diffs2 and this R, but the good thing is that if we look at the bulk, so if we go to the bulk and we study what's the algebra of this guy SL2R, so there we are going to see that this dr directions play some role. So one way to see is that in 4 dimensions, so let me move this even further. So in 4 dimensions, what happened to who are generators of SL2R. So the generators of the SL2R part of this whole group of transformations are exactly UDR minus R du, du dr, then you have R du, and then you have U dr. So these are this is U and this is dr. So these are the generators of this part of the thing. And this is kind of the usual thing. If you call it this EF, then you recover the usual brackets between these guys. And we know that once you have SL2R, then you can do the usual extension with differential operators to obtain Virasoro, because once you have SL2R, you do this grading by the differential operators and you have Virasoro. So in some sense, it is there, buried within the bulk, waiting to be pushed. But if you push in this way, using diffeomorphisms, what you are going to obtain is the algebra of diffeomorphisms. If you want to
So,
obtain the Virasoro algebra, you have to do a little trick.
so you will get SL2C, but not the extension that is the Virasoro part, right?
No, just the
Or something like that.
SL2C. Just the SL2C.
But
If you
you
want
have
to,
okay, you have two copies of SL2R, right?
you have
In the bulk.
in the bulk. Well, yes, you see, you have one copy from
You have
in the group
SO2 and the conjugate SO2.
SL2. Yes, yes, yes,
This is one of the two, right? This SL2R is one of the two.
one of them.
You can have the other one, but you don't see the extension that will be the Virasoro part of
Exactly.
each SO2.
Yes.
Okay,
You,
okay.
you,
Thank you.
you are not seeing it right away. And that's the interesting part of the things, because this last works in this area, which relate these symmetries at null infinity with the W1 plus infinity algebras. So when you have the W1 plus infinity algebras, you are in a particular, very fine-tuned subsector of all the possible things that you can have at null infinity. So they take, for example, the holomorphic plus one component anti-holomorphic, and then you can do the computation and obtain the W1 plus infinity, but it's a very particular sector of the whole symmetries. And the construction of that symmetry requires certain pseudo-differential operators. And those pseudo-differential operators come from the fact that you have to integrate the equations of motion along scribe plus. So in some sense, since you have these W1 plus infinity symmetries at scribe plus and you can recover them, then it would be really nice to have a description of them in the bulk, or at least a prescription of how to go from the bulk to the scribe plus and recover the W1 plus infinity.
Thank you.
Yes. I don't know if
And may I ask
yes.
a related question? Yeah, and is this know how to do? I mean, this last question that you posted.
Yes. How to do? I mean, if it
How
is
to report
done.
the only one. Right.
Okay, so the W1 plus infinity is it is established symmetry at null infinity. It was done by Laurent, Friedel, and et al. So there are a lot of authors that have worked on that. But how to go from the bulk to scribe plus and kind of how to dig the W1 plus infinity from the bulk, I think that this is not done. So, and it would be really nice to have. It hasn't been done.
Yes, no, it has not been. I see.
Yes, because you have to be pretty careful in the way that you push the things to scribe plus. So the way that you treat these divergences is crucial in which is the final symmetry that you obtain. And besides that, the W1 plus infinity that they obtain is usually like in a very in a very close sector of the theory of all the possible symmetries. So yes, it's not that easy.
I'm right, but I'm asking because this symmetry you also see in theories of higher spin. I mean, if you have something
Yes.
like Jane-Simon's theory in 3 dimensions with a gauge group which is SLN or SL infinity actually. You need to take SL infinity.
Okay.
Then you can this analysis that you're doing, the asymptotic symmetry algebra, and you hit a W algebra at the boundary after doing some reduction, something that is related to what you are saying. The infinite so-called, I mean, it's just a name. Doing what you are doing, essentially with some boundary conditions.
Okay, nice. I haven't seen that.
But in here, in your case, it's more interesting because you are doing it, you can come from a physical theory. I mean, what you're doing, you can start with a theory without any higher spin. In
Yes,
principle, any higher
you just have all the symmetries that act at one corner and see what's the
and still you're saying that there is something there that gives you this symmetry in the sky.
yes.
Very interesting. Very
So
interesting.
yes, it's like an underlying thing that comes just from saying, okay, we have a geometry and we have some corner and we want to see which are the symmetries that preserve the corner structure.
Right, but it's more than that, no? Because I mean, for instance, if you start from Jan Mill's theory, you can do the same thing, and you should have something that gives you this W. This should be some symmetry in the theory. So once you do this expansion of the phase space,
Yes,
to give you some symmetry of
yes.
the physical theory. It's a physical theory. It's not just anyway. Just a
But no, but it's really nice. Do you have any reference for this three-dimension Chern-Simons thing?
the higher spin. Well, this Vasiliev
Okay.
theory. And I think that there is a paper by Tyson and collaborators in which essentially they get the W infinity from the asymptotic symmetry algebra.
Nice.
Tyson and someone else, which I forgot.
Okay. I'll take a look at them.
I can send you.
Yes, if you're
Thank you.
kind enough. Yeah, thank you. Yes, exactly. So in Young Mills, one can go from the bulk to straight plus, and you have this via this Tuchel field, and you can do all this tension and you can recover things. But there is a missing step in there, which is okay, you have to relate precisely the things in bulk and straight plus, which this group tells you that something is missing already. You have this nice structure, and it would be nice to have the corresponding thing. So just to continue, so what we want to do is to study this group when we go to straight plus, and for that we are going to need what is called the embedding maps. So embedding maps is the following. So let me show you this nice picture. So we have our diamond here, and with the corner Z and some close Cauchy surface, and we act. So we can have this, as usual, this two point of view of if we act passively with a diffeomorphism or actively. So in one way, we can say that we act with a diffeomorphism and the diffeomorphism change the structure, or we can say that we have an embedding from some fixed manifold, and the embedding goes to the space-time, but the embedding is field dependent. In what sense is field dependent? That it depends in which point of the solution space we are standing. Okay, so one way to say is you have a diffeomorphism that contains certain degrees of freedom, and it acts on this structure, this null structure. Or the other way is to say that we have an embedding, but the embedding changes depending on in which point of the solution space you have. So those are two things to say the same. And when you act with a diffeomorphism, each point in the null structure, each point, so let's assume that we are here in Y mu, this point will be moved away infinitesimally by some vector, which we call chi mu, and this chi mu depends on the diffeom. But also, if we consider the embedding of the surface, we consider the embedding, this also will be moved by the same chi. So at the end of the day, the only thing that matters is this vector and how we interpret this vector. If it is coming from an embedding of a diffeomorphism, won't make the difference. So just to make clear, here in blue, we have some reference embedding, and in black, we have the new embedding. And the difference between them is this, well, the variation of those two embeddings is this chi mu. Okay, so for that, you can see later in the notes, there are a lot of computations, there are a lot of things to unpack, but the main thing that we have to take home from this is that once we take this diffeomorphism, so we have the solution space, let's draw here solution space, and we have some point in here. We were going to have some map from solution space to the possible embeddings from our manifold here. So we will take this nice pi times S2 to the space-time. So for each point of the solution space, we are associating one embedding. Okay, so that means that the embedding is field dependent. So it depends on the configuration that we are considering. And the advantage of having this is that we can do all the symplectic study of any integrated Lagrangian. So we start with the Lagrangian, we start doing this symplectic potential, symplectic form, and we will arrive at a symplectic form that depends on the integrated along the three-dimensional surface plus an extra term, which is the corner term, which will be in here. Okay, so that's what we are going to do. I mean, I'm just going to say the results, but you can read it in Doran's paper, in Lucas' paper. Those are really nice, like really nice explained. So the main thing in this, the main thing with this construction, so we will have a map, which we call it, let's call it G, which takes a solution and gives you an embedding map. Okay, and this map will have a differential, which we'll call it chi. Chi takes some tangent point in here and gives you a tangent point in the embeddings. So chi will be tangent points on solution space to tangent points on embedding space. So when things start to get this abstract and this mathematical, the nicest way to do is to do a draw and rely on the draws, of course. And so since we have a manifold of solutions and we are going to the manifolds of possible embeddings, the differential of this map will take a tangent point in solutions and give you a tangent point in embeddings. But tangent points in embedding space, it's just how to relate infinitesimally to embeddings, and that is exactly the vector chi, which relates one embedding to the other. So it's kind of the generator of the flow from one embedding to the another. So that means that this particular object, which is the differential, we can write it as, so it will take some tangent in the solution space, which we call like this, and it depends, of course, in the map, and it will be the differential of the map G respect to the flow of delta phi on solution space times G minus 1 of flow over as the same. You understand? There you go. So that's the thing. So what we are doing is taking the map, taking the derivative at t equals 0, multiplying by g minus 1, and what we obtain is one form in solution space, which will give us a vector on embedding space. Okay, so this is what is called an field-dependent embedding map, because it gives you start with a variation tangent to solution space, and it gives you a vector on the real space, so Minkowski or whatever manifold you're working with this guy. what we could do now is, okay, I have a Lagrangian. So if we start with a Lagrangian, so let's call S of some the Lagrangian, it will be like the integral in some domain of who. So now is that we have to take a choice between if we are taking the passive view of point of diffeomorphisms or the active viewpoint of embeddings. And those two are completely equivalent modulus some boundary terms that we are going to see. So one prescription is, okay, you take the pullback of the Lagrangian over D, okay, and the Lagrangian depends on the field configuration. So this is one of the prescriptions, one prescription. Two. And the other prescription is, as you can see, is that S will depend on the Lagrangian and on the map, and it will be the integral in D of the Lagrangian of the pullback of the field parameters. Okay, so those are completely equivalent, modulus some boundary conditions. And the thing is that first is that, okay, you have some region of space-time and you want to integrate something, what you do? You can integrate and then apply the embedding map, or you can apply the embedding map and then integrate. Okay. And if we go through this path, what we are going to obtain is that, so in prescription 1, we have that the symplectic potential, so the symplectic potential, let's call it like a tilde, will be the usual symplectic potential is the symplectic potential computed in a Cauchy surface, plus some combination of the Lagrangian density with this chi. So you have to remember that this chi is the differential of this embedding map, but the end result of this guy is that is a vector on space-time. So this is actually a vector on space-time, which depends on G, on the embedding map. Okay, but it is the Lagrangian is a 4-density, so here we have a 3-density. It's integrated along some Cauchy Haber surface, so it's pretty straightforward. The computations, of course, are not straightforward. One has to sit and really look at the things and the definitions, but in the end, what one has is this, that this is the usual symplectic potential, and then we have this extra thing that comes from considering field-dependent embedding maps. So what happens when everything is fixed? So we fix the gauge, and the fall of conditions, we say, okay, the round metric is the one that is fixed at scribe plus. So that means that no embeddings, so this guy is 0, and therefore we only obtain the usual symplectic potential. But now, since we are moving the possible spheres at scribe plus, then we have to take into consideration moving the spheres. So, for example, the Geroch tensor that we reviewed yesterday. So that is the contributing term from here. If we do the same, but with the second prescription, what we will obtain is that, let's call theta again, but it's just a matter of names. We obtain is theta plus the same thing plus the Q associated with this guy. So this is the nether charge associated to the vector coming from for varying the embedding maps. So again, we see that we have the usual symplectic potential. We have this extra term responsible for the changing in the degrees of freedom in the boundary, and then we have this, which is the differential of the charge associated to this vector. And as you can see, like intuitively, this is saying that, okay, to the usual symplectic potential, we are adding now this extra term, which has the information of the charge for this vector, okay, which is the differential of this. Okay, so both approaches are the same, modulus this dq, okay, so this q is the kind of the difference, and we can gauge it away, or we can kill it by some appropriate boundary conditions, okay? And so one can compute, of course, once you have the symplectic potential, you can compute the symplectic two-form, so symplectic two-form, and this was done, for example, for the case of gravity in the papers of Laurent. So if we compute the covariant derivative, if we compute the exterior derivative of this expression, which is a nasty expression, it will be the following. So we have the integral in some surface. Then we have the pullback of this map with the exterior derivative of theta, plus on the boundary of the pullback of the following. So here we will have some extra things. Let me write it. Plus the derivative of u g. So this is the Lagrangian. Let me write it like this. This is the derivative. So what does it mean? So if we take this expression from the second point of view, and we compute the symplectic two-form, what we are going to do is compute the exterior derivative of this object. Exterior derivative in solution space. When we do that, we have to integrate over a three-dimensional surface. That's called I, just to then make the same thing in square bracket. We can call it sigma if you want. So the first term is the usual contribution of the symplectic potential. But now we have all this stuff coming from the boundary. So it's a corner term. And these terms depend on the differential of the embedding map procedure. So here we have the inner product of the symplectic potential with this vector field. Then we have the Lagrangian density with these two contractions. Then we have the Lie derivative of this charge. Okay, so it contributes in a highly non-trivial way when you compute this embedding, the differential of the embedding map. And the important thing is that we can do this for any Cauchy surface, and we can push the Cauchy surface all the way to infinity. Okay, so in the end, what we can do is take.
Sorry, may I ask a question? May I ask
Yes,
a question? The second term, why is not zero? Because you are contracting with the same vector, or no?
Yes, so that's part of the computations that I didn't do, but you can see in the notes that this vector is not it lives in the B exterior algebra, so the grading of those algebras is different as the usual wedge. Yes, so they are commute, so they are not defined as exterior algebra per se. It's an Ehresmann exterior algebra. So instead of
they are Grassmann or something like that.
Yes. They are Grassmann objects. So when you put the wedge or the commutator, it changes the sign of the -1. So.
Okay.
Yeah. No, but I mean, this is part of the complications of this stuff. Yeah. So, Matthias, yes.
Yeah, Javier, this embedding procedure is unique, or you can embed in many ways?
You can embed in a lot of things. So you actually will have some residual gauge within the embedding map. So
thi-
for yes,
yeah. So these are like edge modes, things that live in this edge.
yes, they are. These
So
are edge modes.
yeah.
Yes.
So how do you know which embedding map you should use or is a matter of choice?
I only have a few examples to discuss, and I don't
Okay.
know. Yes. So, for example, in the case of gravity, we know that the embedding map is just changing the sphere. And if you take these diffeomorphisms that only change the sphere, then you recover the usual symplectic structure, which is what we did with Miguel Campillo.
Okay. Okay, thank you.
And yes, that's all. So there are no more examples that I am aware of. Okay, that I'm aware of.
But a very important one.
Yes, it's at least it's a sanity check for you, you know. So yes, and yeah. So when taking this limit and going to Scribe Plus, then you carry all this information with you, but it's still you have it in the corner, and this was done by damage compare. Oops. Compare, and they compute the renormalization of this procedure, and they obtain the correct. Well, I mean, they obtain some charges. Those charges happen to be the same as Miguel and I, and Alok and Friday, so they are consistent with everything.
Okay.
Just a quick note regarding this symplectic form. So one natural question is whether these charges that one compute are integrable or not. Okay, so there are a lot of sources for non-integrability in this symplectic form. Again, with suitable boundary conditions for the UD case, one can kill certain non-integrabilities at Scribe class. But it was shown by Luca Cembelli and Robert Lee that when you have a finite surface and you have this expression of the embedding maps, then the result that you have from this point of view, so you are thinking the things from embedding point of view, so the result that you have is charges that are integrable, okay, in the usual sense. So you can write, so you have the closure of the brackets. So QH1, QH2 will be QH1, H2, and these charges you can integrate them. So you have the famous equation. So this is okay within this perspective, and that's why it is useful, because it gives you a prescription of using these embedded maps. It gives you a prescription of how to construct this extension. This extension is consistent, but we know so far going to Scribe Plus, and also it is a nice expression for the charges because they are integral. Okay, so that's kind of the main takeaway. I don't know if anybody has some questions so far.
Oh, yeah, I have a question.
Yes.
Hi, Javier. Just one little thing that was coming to my mind. I mean, there are these papers by Mark Gayler where he talks about gate edge modes for gravity and Trent-Simons. And I don't know if I'm right, but is this a Stuckelberg trick that you're applying? Is what he calls, I mean, like introducing this edge mode that is a field-dependent gauge transformation would be?
Yes. Yes.
That's the thing.
It's equivalent. Yes. And there's also another name for these edge modes, which are Goldstone modes.
Those are the Goldstone modes from celestial holography, you mean? The ones that come out?
Yes, because you add them to the thing like dressing the Lagrangian, you add them and their actions just resembling the Goldstone modes. What else?
Okay, and this freedom of embedding that you were talking before is what, for instance, he refers to as these different ways you can introduce either bulk or boundary fields, degrees of freedom that will end up recovering you these gauge invariants or of some sort. Yeah.
Yes, exactly. That's the main property. And
I see.
yeah, it's good that you mentioned Mark, because together with Mark, Silvia Nagy, and a student of hers, Giorgio Pizzolo, we are trying to make sense of this expression. So when you have G equal E to the some diffeomorphism, and you act on the base metric,
Mhm.
you can do it as long as you are for the diffs2. That's what we did with Miguel. But if recovering larger gauge transformations, so for example, what happens when you have an order r to the power of n, large gauge transformation. So you have it in the bulk, you can do it, you can do this finite diffeomorphism on the bulk. But what happens when you push it to Scribe Plus? Do you obtain consistent ER world charges? Do you obtain similar expression? Or what happens with this? And we are kind of work in progress on this direction.
I see. That's really interesting. Yeah. Thank you very much for the clarification.
No. Thank you for staying. So some future, I don't know how much time do I have.
Time is more or less over, but I mean, you can go a few minutes.
Oh, okay. So, yeah, just so 2 or 3 points about open problems. And
Excellent.
yes. So one of open problem is this one, which Fernando has just asked, how to relate for higher order symmetries. The other point, of course, was the thing that we talked before. So we have this W1 plus infinity algebras from conformal field theory. And it was recently discovered that, well, starting in 21 with Stromlinger's paper, and then all those papers that come after it, that they kind of found this W1 plus infinity at Scribe Plus for symmetries of gravity. And it would be nice to have a nice description of how to take from the bulk to the Scribe Plus a subsector that gives you the W1 plus infinity, because it seems that information is already buried inside the diffeomorphism, the higher order diffeomorphism group acting on the corner. So it would be nice to have that. Besides, all the construction only of these algebras is kind of quite complicated, because you have to go to the spin algebras, and then you have to go this diagonalization with some limit of an arbitrary deformation parameter, and yeah, it's kind of difficult to have a grasp of these algebras. And the other thing that it would be nice to see is the impact of this construction of the Zuckerberg field. So in the double copy maps. So in that sense, there are some subtle clues that you can have some information regarding double copy for gravity and Young-Mills using this Zuckerberg trick, and that's part of the thing that we are working with Mark and Silvia, because when you have this Zuckerberg field, you obtain a parametrization of the phase space that contains only even powers of certain object. And if you have that Young-Mills correspond to half of the integers, then automatically you think, oh, okay, so if I take the double copy of this, suddenly I will have the whole integers. So there is some slight clues that we are working that point towards these double copy maps between gravity and Young-Mills. In the self-dual case, we already did it with Silvia. It was super compact result, because for gravity, I mean, in self-dual gravity, this e to the d is automatically, I mean, you can do it finitely, in finite many places, so it was close. But we want to work whether, we want to know whether it could be extended to all orders, or how to do it. So yeah, that's it. Of course, there are many other applications and many other possible lines to research, but these are kind of the three that I'm interested most at the moment. So yeah, I think that's it. Thank you for your attention.
Thank you very much, Javier, for the lectures.
Thank you for these days and the opportunity to talk.
So I guess we have time for some questions, comments. Go ahead, Matthias.
Yeah. So I very like lectures, Javier. And also, how is there a way to relate this corner algebra to the Carolian thing people work to?
I'm pretty sure that there is a way. I haven't studied it, but you know, there are all these papers by the perimeter group that they study the Carolian fluids and how they are related with gravity. Even I think that some months ago there was a paper published by Luca that kind of is a nice starting point to read those things. So. I have I mean, I haven't studied the Carolian fluids.
Yeah. Okay, thank you.
No, you're welcome.
May I ask a question? Thank you,
Yes.
Javier, for the lecture. Well, super nice. Do you know if this, in some sense, can be extended to other dimensions, like higher dimensions or something?
Well, this embedding map stuff is pretty general, so they did it for general things, but it would be nice to see if you can extend it for. I mean, you can have an arbitrary topology or whatever, and see what yeah. But at least for what I know, it's just 4 dimensions. All the details are being studied in 4 dimensions, but some generalities can be said about greater dimensions, of course. Yes.
Okay. And other question: when you say that you move the sphere, you mean that you are deforming the sphere, or moving like in the radial coordinate, something like that?
Oh yeah. So you want the sphere to be fixed and only act upon some conformal variations. So but
so it's round, always round.
Deform, yeah, always like deforming the sphere, but in the same place. But if you impose that, then those deformer systems naturally will have some extra. They will generate some extra directions, and one of those directions is the du, and the other one is the db. You cannot escape the moving along null geodesics.
Okay. Well, thank you.
No, you're welcome. Yeah. Okay, I see the things that Alejandro sent me, so thank you, Alejandro.
Thank you. No, congratulations. Very interesting.
Yeah. Well, thank you.
Well, if we don't have more questions, let us thank Javier again. I don't know, Lucas, how do we follow now, Matthias?
Yeah, maybe we can have
can
5
take
minutes.
5 minutes. Yeah.
Yes, and so we still have the 10-minute delay. So
okay.
yes, it's at 15. We come back.
Okay.
I see Pedro is here. Yes. Okay.
Yeah.